In this video, we're going to continue on with some calculations related to the gas laws. And in particular, first we're going to start with dealing with some stoichiometric relationships. So of course we can relate stoichiometry to anything. In this case, we're going to relate it to the gas laws. So we've got an example problem here. The reaction used in the deployment of automobile airbags is the high temperature decomposition of sodium azide and NaN3 to produce N2 gas. And we want to know how many liters of N2 at 1.15 atm and 30 degrees Celsius are produced by the decomposition of 45 grams of NaN3. So we have pressure here, and we have temperature, and we want to find volume, but we're not given the number of moles. So you see pressure and temperature, and you know that you want volume, and you only have one gas you're dealing with. So you would think you would use PV equals nRT, except for the fact that we're missing the number of moles. But we do have a way to find the number of moles, because we're told that we have 45 grams of sodium azide. And we know that the N2, the pressure and the temperature are given for N2, and we want to find volume for N2, which means that we need to get the number of moles of N2. And fortunately for us, we have a way of doing that since we can use our stoichiometry. So let's start with the 45 grams. And we need to convert grams to moles. So if you calculate the molar mass of sodium azide, it comes out to 65.02 grams of sodium azide per 1 mole of sodium azide. And then we can look at our reaction here, and for every 2 moles of sodium azide, we get 3 moles of N2. So if we take 45 times 3 and divide that by 65.02 times 2, we come out with 1.04 moles of N2. So then we can take that and plug this in to our ideal gas law along with the pressure and temperature and calculate the volume. So we know that we're going to have to convert 30 degrees Celsius to Kelvin. So 30 plus 273 gives us 303 Kelvin. So I'm going to go ahead and go to the next slide, a blank slide here, so that I have room to work this out. So PV equals nRT. And we were given a pressure of 1.15 atm times the volume is equal to, we calculate 1.4 moles times R over Kelvin times mole, and we have 303 Kelvin. So we divide both sides by 1.15 atm to get volume by itself. And the volume is then equal to 1.04 moles times 0.0206 times 303, divide that by 1.15. So if we divide that out, that comes out to 22.4 liters. So let's take a look at another example here. We have quicklime calcium oxide is produced by the thermal decomposition of calcium carbonate, which is CaCO3. And we want to calculate the volume of CO2 at STP produced from the decomposition of 152 grams of calcium carbonate by the reaction that we're given here. So again, we have the grams of calcium carbonate, but we want to calculate volume of carbon dioxide. Now, one thing to notice here is that we are at STP. So if you recall from an earlier video, at STP is 1 atm and 273 Kelvin. So if we are at STP, we determine that 1 mole of gas has a volume of 22.4 liters. Now this is only true when the pressure is 1 atm and the temperature is 273 Kelvin. If this is not the case, this relationship no longer applies, because the calculation to get this volume uses this pressure and this temperature. So if we have a different pressure or a different temperature, we can no longer say that 1 mole equals 22.4 liters, which is why we couldn't use that equality in the last problem. But in this problem, we have the luxury of being STP, so we actually can avoid a little bit of extra work here at the end of our problem. So we're going to start with 152 grams of calcium carbonate. And if we calculate the molar mass of calcium carbonate, that comes out to 100.09 grams per 1 mole of calcium carbonate. And then according to our reaction, 1 mole of calcium carbonate reacts to form 1 mole of CO2. And then we want the volume of CO2, and we know at STP that 1 mole of CO2 gives us 22.4 liters. So 152 times 22.4, and we divided it by 100.09. .0 liters of carbon dioxide. So we also need to talk about gas density. So density can be calculated from the molar mass, and in this case using the molar volume. So if you think back to way back at the beginning of the semester, we talked about density is equal to mass over volume, and that's the typical definition that we use. I'm not going to go through all the algebraic derivation here. The key part of this is that the density of a gas is equal to the pressure times the molar mass over the gas constant times the temperature. And in this case, pressure has to be in atm, and temperature, as with all of the gas laws, has to be in Kelvin. And when that is the case, it comes out that density for gases, this works out to grams per liter. So, there's a lot of factors that depend on gas density. One in particular that we look at is buoyancy. So, for example, if you're going to do something like try to fill up a hot air balloon, of course you want a gas that's going to be lighter so that your hot air balloon can rise easily. So you would want something more like helium as opposed to something like carbon dioxide. You want something that's going to be light, that's not going to weigh your balloon down. So gas density depends on the molar mass and the temperature, which is why if you look at these gases, the molar masses of these gases would increase as their density increases. So density depends on molar mass and on temperature. So as density goes down as temperature goes up. Let's take a look at an example here. The density of a gas is measured at 1.5 atm at 27 degrees Celsius and found to be 1.95 grams per liter. And we want to calculate the molar mass of the gas. So we know 27 degrees Celsius, we've got to convert that to Kelvin. So 27 plus 273 gives us 300 Kelvin. So if we take the density of a gas, density is equal to the pressure times the molar mass over the gas constant times the temperature. So we're given a density of 1.95 grams per liter. And we're given a pressure of 1.5 atm. And we want to calculate the molar mass. The gas constant is still the same gas constant that we've been using. Kelvin times mole. And our temperature is 300 Kelvin. So if we rearrange this algebraically, we get 1.95 grams per liter times 0.08206 liters times atm over Kelvin times mole times 300 Kelvin. And then we divide both sides by 1.5 atm to get molar mass by itself. So molar mass is equal to 1.95 times 0.08206 times 300. Divide that by 1.50. So we get a molar mass of 32.0 grams per mole. Okay, so let's talk about Dalton's law and partial pressures. So Dalton's law of partial pressures tells us that if we have a mixture of gases in a container, the total pressure exerted by that mixture is equal to the sum of the partial pressures of each of the individual gases in the container. So if we take each of the gases, we can represent their partial pressures, and that's equal to P total. So the mole fraction is also another way that we can use Dalton's law. we know from earlier in the semester when we talked about different ways of measuring concentrations, mole fraction is equal to the moles of a component over the total moles in the mixture. So if we take mole fraction, which is represented as X, and I represents the component we're talking about, so the mole fraction of the component we're talking about is equal to the number of moles of the component divided by the total number of moles. So for gases, we can also write that as mole fraction is equal to the partial pressure of the component we're talking about divided by the total pressure. So let's take a look at some examples here. We have mixtures of helium and oxygen can be used in scuba diving tanks to help prevent the bends. For a particular dive, 46 liters of helium at 25 degrees Celsius and 1 atm, and 12 liters of oxygen at 25 degrees Celsius and 1 atm were pumped into a tank with a volume of 5 liters. We want to calculate the partial pressures of each gas and the total pressure in the tank at 25 degrees Celsius. So we're given two separate gases here. We're given helium and oxygen. And at first we've got 46 liters of the helium at the given temperature and pressure. And we've got 12 liters of the oxygen at the given temperature and pressure. And then we have those two gases put into a tank that's a different volume. So the first thing we have to figure out is how many moles of each of these gases was put into the tank at this volume. So I'm going to go ahead and rearrange since I'm going to be doing a lot of calculations here. I'm going to go ahead and rearrange this equation for the variables that I need so that I don't have to do quite so much writing later on. So the first thing I'm going to need to be able to calculate is the number of moles. So I'm going to rearrange this equation for the number of moles. So the number of moles is equal to PV over RT. So we're going to calculate the number of moles of helium and the number of moles of oxygen. So the number of moles of helium, we're given a pressure of 1 atm, and a volume of 46 liters. And we have the gas constant, which is 0.08206 liters times atm over Kelvin times mole. And we're given a temperature of 25 degrees Celsius, which is 298 Kelvin. So if we take 1 liter times 46 divided by, 1 atm times 46 liters divided by 0.08206 times 298, and we get 1.88 moles of helium. And then we calculate the number of moles of oxygen. We have again 1 atm but we have 12 liters. Divide that by the gas constant. So if we multiply 1 times 12 divided by 0.08206 times 298, that comes out to 0.49 moles of O2. So the next thing we need to figure out is what the partial pressures are for both helium and oxygen. So again, I'm going to rearrange the gas law, the ideal gas law, to get, this time, get pressure by itself. So that I can calculate the partial pressures of each of those in a 5-liter tank. So I'm going to go ahead and go to a blank slide here so that I have enough room. So the partial pressure of helium, we've now taken it in a 46-liter container, from a 46-liter container and put it into a 5-liter container. So we're going to take the 1.88 moles of helium that we calculated times the gas constant times 298 Kelvin and divide that by 5 liters. So if we work that out, it comes out to 9.2 atm is the new partial pressure for helium. So then for O2, we're going to do the same thing. We're going to take the number of moles that we calculated and plug that into the ideal gas law. And divide that by 5 liters, which is the new volume. And if we work that out, we get 2.4 atm. So now we can calculate the total pressure. So the total pressure is P total is equal to the partial pressure of helium plus the partial pressure of O2. So if we take the 9.2 atm that we came up with plus 2.4 atm, that comes out to 11.6 atm as our total pressure in the container. And these are partial pressures for each gas. So let's take a look at another example here. The partial pressure of oxygen was observed to be 156 torr in air, with a total atmospheric pressure of 743 torr. Calculate the mole fraction of O2 present. So we have the partial pressure of O2 and we have the total pressure. So we can use our equation from a couple of slides ago. And we plug in the partial pressure of oxygen and divide by the total pressure, which is a 743 torr. So if we divide that out, that comes out to 0.210. And mole fraction is unitless because the units cancel each other out here. So we have a mole fraction of 0.210 here. So we're going to go ahead and stop here, and we will get some more practice with this in class.